numbers we plugged in. An indefinite integral means we're not actually plugging in and evaluating. So when you do those antiderivatives, what do you have to make sure you have at the end, Landon? Plus C, yes. So just more practice with that. I'm really not going to talk about that. So let's just do some problems. So if I want to evaluate 10x to the fourth, the integral of 10x to the fourth minus 2 secant squared x dx, what should I do? It's the antiderivative of 10x to the fourth. 2x to the fifth minus 2. What has a derivative of secant squared? And what do we need at the end? Okay. Let's do a more challenging one. Integral of cosine theta over sine squared theta d theta. Can we do the antiderivative of a quotient like that? No. So it's not really obvious right now where I'm going to go with this. Let's see if we could rewrite it at all. Sine squared, this is where those trig proofs come back into play. Remember where you had to rewrite all these things using all these formulas? Sine squared theta means you have two sines on the bottom. Okay, you may not need this step, but I'm going to go ahead and show you. So I could write that as a 1 over sine times a cosine over sine. So far, so good? What's 1 over sine? Cosecant. What's cosine over sine? Cotangent. Okay, so all I did was rewrote my quotient as a product, but do we know of anything that has a derivative of cosecant cotangent? Okay, what's the derivative of sine? Cosine, derivative of cosine. Negative sine, derivative of tangent. Derivative of cotangent. Negative cosecant squared. Derivative of secant. Secant tangent. Derivative of cosecant. Negative cosecant cotangent. So since I don't have a negative, this would be a negative cosecant theta. And then what else do we need? Plus c. All right. Why don't you guys do the next one? Antiderivative of x cubed minus antiderivative of 6x So 3 to the fourth is 81 over 4. 3 squared is 9 times 3 is 27. Minus, if you put in 0, you get out 0. And so you get a negative 27 over 4. Let's do an uglier one. 2x cubed, we can easily do the antiderivative of that. It would be 1/2 x to the 4th minus the antiderivative of 6x, 3x squared, plus 3 over x squared plus 1. Think of that as 3 times 1 over x squared plus 1. 1 over x squared plus 1, that was on that problem 39 last night. What's the antiderivative of that? Tangent inverse. Again, we couldn't evaluate that without a formula because you can't do the antiderivative of that quotient. So, now we can plug in. 2 to the 4th times 1/2 would be 8 minus 12 plus 3 tangent inverse of 2 minus, we put in 0, we get 0 plus 3 times the tangent inverse 0. I think it's finally raining. Tangent inverse of 0. That's like saying tangent of what angle equals 0? Tangent of 0 is 0, so that's a 0. So this is my final answer. We don't know off the top of our head when tangent is 2. That's not a nice one that we have memorized, so I would just leave it like that. Antiderivative as the quotient? No. So what do we have to do first? Simplify everything. Okay, 2t squared over 2t squared is just 2. T squared, square root of t. What is that? T to the square root is like a 1/2, so that's t to the 3/2 over t squared. So if you subtract those exponents, 3/2 minus 2, you get -1/2. Minus 1 over t squared, that's t to the -2. So an antiderivative of yes. No, wait. Yes. Sorry, it's not 3/2 on top, is it? It's 5/2. So 5/2 minus 2. Sorry about that. So antiderivative of 2 would be a 2t. Plus, if you add 1 to this power, 1/2 plus 1 would be 3/2. So what do you put in front? Okay, add 1 to this power, and that's a -1, so we need a -1 in front, which just makes that a positive. So then let's plug in. If I put in my 9, 2 times 9 is 18. All right, no calculators. 2/3 times 9 to the 3/2. How do I redo that 3/2? What does that mean? Square root of 9 cubed. What's the square root of 9? 3. 3 to the 3rd, 27. So 2/3 times 27 would be 18. 9 to the -1, a negative power just moves it to the bottom. Put in a 1, we get 2, 2/3, and a 1. arguing with me? I don't know what that is. That's this one. Questions on any of these integral problems? It's really just more practice with the same thing that we've been doing. The second thing that I wanted to talk about here, some of the applications with these integrals. So, we know that a derivative represents the slope of the tangent line. So a derivative is a rate of change, right? If we had, we tip over my water cup and we measure the rate at which water is coming out of my cup. That is the derivative, the rate the water comes out. If I knew that rate and I did the antiderivative, what that tells me is how much water has leaked out of my cup in a given amount of time. So a derivative is a rate of change. The antiderivative is like net change. It's the overall change in our amount. So the next few slides just have some examples of when this is used. First one I had, kind of like the example I just gave. If you have the volume of water in a reservoir, and the derivative is the rate at which the water flows into that, then the antiderivative would be the change in the amount of water. If we had the concentration of the product of a chemical reaction, then the derivative is the rate of our reaction, so the antiderivative would be the amount of change in the concentration of our product. Okay, how much of it has grown or decreased in that amount of time. Linear density, if you have the mass of something, the derivative, the rate of change of that mass, is called the linear density. So the antiderivative would be the actual mass between 2 points. If we're talking about population growth, this is one that we've used before. We talked about the derivative is how that population is changing. So the antiderivative would be the actual amount. How many people have we gained or lost in that amount of time? We've talked about marginal cost and cost a lot. So the derivative is the marginal cost. Then the antiderivative would tell you the actual change in the cost. Not how the cost is changing at a particular point in time, but the actual change between 2 points in time. Do you guys see the difference there? We've talked about position, velocity, acceleration. So if I have a position function, we know the derivative is the velocity. So if I did the antiderivative of velocity, I get the change in my position. Now if it's traveling at 3 feet per second, and I integrate and I get 5, that tells me it's actually moved 5 feet during that amount of time. There is also, we need to differentiate between displacement and distance. They are not the same. Displacement, remember we talked about if you're looking at areas of a curve, things above the axis are positive and below is negative. Okay, if I were to, let's say, take a pencil, I start here, I roll it to Peyton, and she rolls it back to me. Displacement, so it started here and it ended here. My displacement is 0, because it is exactly where it started. But if I wanted to know the total distance that pencil has traveled, is it a distance of 0? No, it traveled her and it traveled back. So if I want like distance that has traveled, we need to do absolute values. We don't want to subtract off when something goes backwards. We want to add that in. But if I want displacement, that's just how far is it from the starting point. Then we don't have to worry about doing absolute value. We just integrate like normal and those negatives will come off. Does that make sense? Alright, so let's look at an example. A particle moves along a line. so that its velocity at time t is v of t equals t squared minus t minus 6, measured in meters per second. I'm going to find the displacement and the distance between 1 and 4. So, if I need the displacement, that's just how far it is from the starting point. So what do I need to do? Just integrate. We're going to integrate from 1 to 4. My velocity, t squared minus t minus 6. We put a dt on the end of that. So antiderivative of t squared is 1/3 t cubed minus 1/2 t squared minus 6t. So if I plug in a 4 cubed, 64 over 3 minus 8 minus 24. And what do we get here? Negative 4.5. Okay, so what does that number mean? So our area under the graph, in terms of this, we're looking at velocity. This is the position. The negative tells us what? It went backwards 4.5 meters. I guess I should technically put meters on that, right? Do we have units on this problem? Okay, B is the total distance traveled. Can my distance traveled be negative? No. So first of all, we need to figure out when this thing changed direction. When did our velocity change from positive to negative? So let's figure out what makes our velocity equal 0. I could do box method with that. Factor into t minus 3, t plus 2. So we get 3 and a negative 2. Can your time be negative? No. So it changed direction at 3 seconds. So just like those absolute values, you always separate them when it equals 0. So that's what we're going to do. We're going to integrate from 1 to 3. And then we'll integrate from 3 to 4. So let's figure out what we need to do here. If I put in something between 1 and 3, so if I put in a 2, I get 4 minus 2 minus 6. Is that positive or negative? Negative. Since I'm doing the absolute value, what should I do to this? Distribute a negative. So I need to make it a negative t squared plus t plus 6. Okay, if I put in something between 3 and 4, or even if I put in a 4, I get a positive, so an absolute value wouldn't change it. Alright, so then if I integrate, plug in 3 cubed is 27 times negative 1/3 is negative 9 plus 9 halves plus 18. 61/6. And we knew that should come out to be a positive. If we got a negative there, that would most likely mean we had our signs wrong on the two original ones. So the total distance traveled, 61/6 meters. So are we clear on the difference between distance and displacement? Last example I wanted to do, I wanted to look at one in the book. You guys would grab a textbook. Okay, so page 403. We have a picture here that shows the power consumption in the city of San Francisco for a day in September. P, that's your y-axis, is measured in megawatts. T, your x-axis, is measured in hours since midnight. Estimate the energy used on that day. Okay, so this is showing me the power consumption. If I want the total amount used, we're really talking about area under the curve, aren't we? Now, unfortunately, do I have just an equation I can integrate? No. So how have we estimated areas under a curve when we couldn't tell exactly?
Rectangles.
Yep, rectangles. We've done left hand, right hand, and midpoint sums. Which one is the most accurate out of the three? Midpoint. Let's do a midpoint sum here. How annoying do we want to be? Do we want to do 24? It's going to be kind of annoying, but it's more accurate, isn't it? We care about accuracy. Cover up the solution there. I don't want you guys just copying down what they wrote. I want to make sure we know how they're getting it. Okay, so what we are going to do, our best guess. We know that the more rectangles we use, the better it is. I think it would be pretty hard to do anything more than 24 here. So we are just talking about energy used in one day, so 24 hours. That seems reasonable. So we're going to integrate from 0 to 24 of this function. And we decided the midpoint sum would be the best. So when we did these, we took at all times the change in x. If we decide that we are going to do 24 rectangles, then my change in x, 24 minus 0 over 24 is just 1. So I just have to take all this times 1. So that's not any big deal. Then we are going to estimate the midpoint of each of those little rectangles. So if you look at your chart, your graph, between 0 and 1, so at about 1/2, what would we estimate that to be? What do you think? 450, okay. So then between the 1 and 2, 425? Okay, between the 2 and the 3. Between 3 and 4, we'll call that 400. Between 4 and 5, 4 or 5 again. We're just getting close here. Between 5 and 6, 450. Between 6 and 7, which is 550. Between 7 and 8, 650. You're being very precise here. Between 8 and 9. What do you think? 750? 14. 14 and 15. 15 and 16. Still 840. 16 and 17. 17 and 18. 70. Where am I at? 18 and 19? What do you want to call that? 705. 19 and 20. What do you think? 700. 20 and 21. 7, what? 80? 90? What? Sorry. What did you guys say? 680. Yep, I was looking at the wrong one. What am I at? 21 and 22. We would be at 22 and 23. What? And 23 and 24. 525. Okay. Is this going to be perfect? No. The book, if you look, they didn't do every 24 hours, they did 12-hour intervals. So our answer should be more precise than theirs. A little more annoying to achieve, but not difficult. We're just reading a graph. And I got 15,770 megawatt hours. The book's approximation was 15,840. So we were pretty close to theirs. Alright. Any questions on this stuff? So that is the end of this section. I am not moving on tomorrow, but what I may do, try to make up some days. So instead of doing like a regular quiz, I'm probably going to give you guys a take-home quiz tomorrow. So you'll have tomorrow in class. This assignment I'm not collecting until Friday. So tomorrow in class you'll get your take-home quiz and this homework, and you'll have the day to work, and then anything you don't have done from the two would be homework. Does that seem reasonable? So both things due Friday.